So in this video, I need to spend some time talking about the principle or the principles behind finding area in polar curves. And what this is really going to amount to is a comparison between the way that we find area in rectangular coordinates, like what we learned last year about finding the area under a curve using integrals, and how we're going to modify those same principles to allow us to find the area inside of these polar curves. And in order to do that, what I have to start with is I have to start by sort of reminding us and thinking about, what's the area of a rectangle with side lengths of x and y? Well, this is an easy thing, right? This would be x times y, right? The thing that you guys are probably less likely to remember is, what about the area of a sector of a circle with a radius of r and a central angle of theta? And maybe pictures here would have been helpful. In this rectangle, I'm talking about, if one side was y and one side was x, the area of that thing is clearly x times y. A sector of a circle means you have some, sector of a circle. That circle has a radius of r and a central angle of theta. Right? Turns out the formula for the area of a sector of a circle is 1/2 theta r squared. Theta, of course, has to be given in radians. If you try and do this in degrees, things kind of explode. But the idea is the area of a sector of a circle is 1/2 theta, 1/2 theta r squared. Okay, now for the mind warping, right? How did we take this and construct the idea of area? What we did back in the day was we said, okay, imagine that I have some function that I'd like to know the area underneath between, let's say a and b. What we did is we actually sort of constructed rectangles underneath this thing. We did these Riemann sums to find out, to approximate the area of the thing. And then in the end we said, well, wait a minute. If I just, recognize that the height of every one of these rectangles is going to be f of x, and the width of every one of these things was going to be dx, I could use an integral to sort of infinitely add up all of these rectangles. And we constructed the idea that the area underneath this curve could be found by taking the integral from x equals a to x equals b of f of x dx. And back when we learned that, I tried to make a lot of noise about the idea that this thing is the area of a rectangle. The height of the rectangle is f of x. Those are the y values. And the width, or the thickness, of each of these rectangles was infinitesimally thin, and that was dx, right? I'm going to do a very similar thing over here for polar. Imagine that I have some polar curve that I want to work with, right? So let's just say, for the sake of argument, that I've got a curve that sort of looks like this, right? And let's say that this curve goes from 0 over to pi over 4. And notice those are theta values. This is like theta equals 0. Oops, that shouldn't be pi over 4. This should be theta equals pi over 2. Right? How am I going to find the area under this curve? I'm going to tell you what I'm not going to do. I am not going to draw rectangles underneath it. And the reason I'm not going to draw a rectangle is that rectangles play really nicely with rectangular coordinates. But in this problem, every one of these points has been found by radiating outward. So what I'm going to do is I'm going to sort of picture for myself, well, I could imagine that there's a little tiny sector of a circle there, and then there's another sector of a circle here, and another sector of a circle, and another sector of a circle. And the idea is, rather than constructing this problem using rectangles, I'm going to construct this area, I'm going to build this area up using really, really, really skinny sectors of circles. Right? So then the question becomes, okay, how do I find the area? How do I do this thing? Well, we can use an integral. We could take our integral and say, I want my integral to go from 0 up to theta being pi over 2. And the question is, what do I need to multiply inside here? Well, what needs to be inside here is the 1/2 theta r squared. But we have to be careful, right? I'm going to put the 1/2 outside because it's a constant. Now the theta, you'll notice that if I was really going to do infinitely many of these sector things, my theta would have to be super, 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 super duper small, just like my x values did here. Instead of using dx, I'm going to use d theta, because theta is going to be sort of the thing that's very small and ranged throughout. And there were a couple of hints that were leading to that. One, remember back in this problem it was x equals a, x equals b, and therefore dx. Over here I have theta equals 0, theta equals pi over 2, and therefore theta is the d theta that I have to use. Okay. The only other thing we need in here is we need r squared. And I didn't actually define a function for this one, but if we had here that r was equal to some function of theta, it's that function, this expression, that we'll be squaring and then working through the integral of. Okay? In the next slide, I'm not actually going to have us compute any of these areas yet, but I want us to sort of look at, if we had an integral, can we construct what the area, what that integral would give us the area of. So what I want us to do in this problem is effectively look at the integral, draw a picture of the curve that goes along with this integral, and then shade in the area that's being talked about. Right. So first things first, hopefully you recognize, there's the half here, there's a radius squared, there's d theta. This is definitely representing an area. We just need to know what this curve looks like. So hopefully you remember from the previous video that 6 cosine theta should look like this. Right? A circle that's set to the right of the y-axis. The circle has a diameter of 6, which means the radius of the thing will be 3. And now, this is asking us to take the integral from pi over 4 up to 3 pi over 4. So what's important for us to do is it's important for us to take some time and look at this circle and sort of figure out where we are at what values of theta. Right? And this is the thing that took us a long time in the previous video. Hopefully we'll do it faster this time. If we evaluate 6 cosine theta for 0, we're looking at an angle of 0, the value we get was 6, so this point over here is going to sort of correspond for us to theta equals 0. Right? If we try another value like pi over 2, right? If we think about 6 times the cosine of pi over 2, 6 cosine pi over 2 is 0, so when I'm at an angle of pi over 2, I'm looking at a point for 0. So this is where theta equals pi over 2. We can probably use that to sort of come back then to the idea that this point up here corresponds to pi over 4, and this point down here corresponds to 3 pi over 4. Right? And that sort of makes sense because if I was going at an angle of pi over 4, I'd get to there. An angle of 3 pi over 4 would be going this way, but the 6 cosine of that is probably negative, and that's what's going to sort of get us back to this value here. So now that we understand that the graph is going in this direction, like this is the orientation of the graph, when we take the integral from pi over 4 up to 3 pi over 4, we sort of imagine these sectors of circles that are being drawn. Right? The first one goes up to pi over 4, and then we sort of, as we go along, we're getting these things. Then we get to pi over 2 where it sort of lands here. Then we keep coming up with more of these sectors of circles going this way. And that section right there, like that thing that I just sort of shaded using these black lines to make the sectors of the circle, that is the area that will be represented by the integral that was given. Okay, so, if we sort of shaded all of this section here in, that's the area that would be found by that integral. Okay, the big thing to come out of this is we have to understand that all of these areas radiate out from the origin. They are not going to be, the rectangles under the curve. It's not about being under the curve. It's actually about being between the origin and the curve. Okay. So here's another example. In this one, I'm giving you, this polar curve, and I'm telling you, that's given by 1 minus 2 cosine theta. I want us to know what this integral is going to give us the area of. So if you're feeling up to it, pause the video, see if you can sort of figure out what the 0 and the pi over 6 represent for this problem. And once you've got that, we can talk about what the area is. So another way of approaching this problem is for us to indeed just evaluate this function using the bounds, using the 0 and the pi over 6, and see what we see. Right? So when I do 1 minus 2 cosine of 0, I end up with 1 minus 2. So this leads us to the idea that when theta is 0, my radius is negative 1. So going at an angle of 0, I go negative 1 units. So this point here corresponds to my theta being 0. I can do the same thing with pi over 6. 1 minus 2 times the cosine of pi over 6. That's going to be 1 minus 2 times the square root of 3 over 2. That's 1 minus the square root of 3. And if we sort of think about that, this is something negative. I mean, if we know that the square root of 3 is 1.7-ish, we get negative 0.7. So we have this idea that when I'm at an angle of pi over 6, my distance is going to be, or rather the radius value is negative 0.7, which sort of puts us somewhere down here, right? So if I'm doing the integral from 0 to pi over 6, I'm sort of radiating out from the origin, right? So we imagine going out from the origin over to 0 and sort of radiating outward until we get to our stop point, and that, little section right there is what's given by this integral. A curious follow-up question is, what integral would I have to do in order to get the entire bottom half of this section? Unfortunately, I'm out of time to cover why, but I'll put this out there and let you guys think about it on your own. Turns out it's going to be the integral from 0 to pi over 3 of 1 minus 2 cosine theta squared d theta. Right? So if we were to use that, we could actually come up with exactly what that bottom half is. I'd encourage you to think about why and try to process that.